So, little bit we have seen that restructured power system, particularly in for the load frequency control, right. So, we have seen that this is that your schedule power flow, that how the actually for two area system, where in both of the areas there are two GENCOs and two DISCOs, right. And this is the expression. For example, suppose if we have say delta PL1 say is equal to 0.1 per unit megawatt, this is say per unit megawatt, delta PL2 is equal to say 0.05 per unit megawatt, right. Delta PL3 is equal to again say 0.10 per unit megawatt, and delta PL4 say 0.20 per unit megawatt. That means this demand, this delta PL1, actually this is the total power demand, that needs for the DISCO 1. So, this is actually for distribution company 1, which in short we call DISCO 1, right. Similarly, for the this is the total power demand required by DISCO 2. So, this is actually for DISCO 2. Similarly, this is for distribution company 3, in short we call DISCO 3, and this is another distribution company we call DISCO 4, right. So, this is the power demanded by the DISCOs, right. Now, you have this matrix CPF element, CPF 13, CPF 14, CPF, I mean how much contact is there these DISCOs with the GENCOs, right. For example, suppose for this example, suppose if my CPF 13 is equal to some arbitrary value I am putting, right, say 10, then CPF 14 say it is 0.20, right. Then CPF 23 is equal to, I mean this one CPF 23 is equal to say 0.10 again, and CPF 24, right, is equal to you say 0.40, right. Similarly, CPF 31 say it is equal to 0, right. Say CPF 32 is equal to say 0.20, then CPF 41, right, CPF 41 is equal to say 0.10, and CPF 42 is equal to say 0.10. If it is so, if suppose, then what will be my schedule type power flow, right. So, that means if you go back to this your DISCO participation matrix, this is your DISCO participation matrix, right. This is your DISCO participation matrix, and what we have taken there, that in this matrix if we put like this, if I rewrite this matrix like this, right, just hold on, I will make it such that everything should be clear to you, right. This DISCO participation matrix, wherever only these elements I will write, because other thing I will not write, only these elements I will write. So, in that case what will happen, that your first thing is that this the way we have written, that your CPF 11, CPF 12, CPF 13 and CPF 14, right. Then this CPF value, that CPF here if you look, CPF 11, 12, 13, 14 nowhere, right, nowhere it is coming, CPF 14 is coming, CPF 13, 14 is coming. So, CPF 13 here say it is 0.10, and CPF 14 it is 0.20. Next you come to CPF 21, right. First let me write down, then CPF 22, then CPF 23, then CPF 24. So, if you come to that CPF 24 is 0.40. So, this is actually CPF 20.40, right. Then if you see here CPF 23 is there, CPF 23 is your your what you call 10. So, this is actually 0.10, right. Similarly, if you come to that CPF 31, right, CPF 31 is given 0.0, suppose CPF 31 is 0, then CPF 32, then it is coming CPF 32, we have taken CPF 32 is 0.20. So, this is your 0.20, then CPF 33 and then CPF 34, right. So, no question of CPF 33 or CPF 34. That means next is CPF 41, CPF CPF41 is equal to, we have taken 0.10. So, this is 0.10. Then CPF42 we have taken 0.10, 0.10. Then CPF43 and CPF44, right. That means when they are your what you call type power schedule equation, you will find in the direction of 1 2 only this portion is coming, and here only these portions are coming. This is related to the DISCO's power demand. Your if any element is there, means DISCO is demanding power, right, from the your what you call from the GENCOs of its own area. So, that means they will never come into the tie line power equation, right. But this one will come, this diagonal one, that means here 1 3 1 4 2 3 2 4 and then 3 1 3 2 4 1 4 2, this one will come in that your what you call in the scheduled tie line power flow equation, right. So, that means, and our this thing is delta PL1 is 0.10, this we have taken, this data you have taken. When you will read this this video, please note down on the notebook, because here then you need not go back to the your what you call next your slide or this, you can do yourself. When you see this, you please note down this data, right. Then what will happen, that your what you call this calculation, that then what is the value of this tie line power flow. So, in that case, this equation that delta p tie or what you call this equation, this one also when you study this, please note it down, such that you need not look into this again and again, you can do yourself. Therefore, my delta PL3 we have taken 0.1, right. So, CF13 0.10, right. Therefore, CF13 delta PL3. So, first term is CF13 delta PL3, CF13 actually 0.10 into delta PL3 we have taken 0.1, we have taken 0.1. So, into 0.1 plus your CF14 delta PL4, CF14 we have taken 0.2, it is CF14 into 0.2 into delta PL4, that means your 0.2 into 0.2, right. Then plus then CF23, CF23 we have your taken 0.10, so it is 0.10, and then your delta PL3 is 0.10, right. Then your CF24, CF24 we have taken 0.4, this is 0.4 into PL4, PL4 we have taken 0.20, right. So, in this case just hold on, this is your PL3 PL4 and this is this one, right. Then minus this is this one, right, minus your CF31, CF31 we have taken 0, it is 0.0 into delta PL1, right. So, PL1 we have taken 0.10, everything is here, everything is given here, everything is given here, right. From there only I am writing. Then plus your CF32 we have taken 0.2, so it is 0.20 into your delta PL2 is 0.05, so it is 0.05, right. Then plus your CPF41 we have taken 0.1, 0.10 into delta PL1 we have taken 0.10, so 0.10 plus CPF42 we have taken again 0.1, CPF42 into your delta PL2 is 0.05, right. That is actually delta P tie 1 2 is equal to, this is your schedule power. Whatever will come, plus minus does not matter. I am to save some time, I am not computing this one here, because I did not do any calculation before coming here, right. So, whatever it comes, if it is positive value, means if positive value of delta P tie 1 to schedule, this means that power actually flowing from 1 to 2, and if it is negative, then power actually flowing from 2 to 1, that is the thing. That is the scheduled power. I mean, whatever they have contracted, according to that this power will flow through the tie line, right. That is two area interconnected by your 3 phase transmission line, we call tie line, right. And whatever will come, that is your scheduled power flow. So, this is the way that we can calculate. Another thing is that what will be the I mean at the steady state, what will be the power generated by your generation companies, GENCO 1, GENCO 2, GENCO 3, GENCO 4, right. For example, so this is I am not computing for you here, it is just you can do it whatever it is, right. So, another thing is that your GENCO 1, suppose GENCO I am making in capital letter, GenCo 1, generation company 1, suppose it's steady state, suppose it is generating power that delta PG1 SS, right, or I can put delta PG1 SS, does not matter. Say GenCo 2, say at steady state it is making delta PG2 steady state, right. Similarly, GenCo 3, it is producing delta PG3 SS, right, and GenCo 4, right, it is your delta PG4 steady state, right. Then what will be the equation then? Suppose this side you will make delta PG1 steady state, delta PG2 steady state, delta PG3 steady state and delta PG4 steady state, right, is equal to that your all that DPM will come, that disco participation matrix, the CPF will come. So, so in that case you write here this matrix CPF 11, CPF 12, CPF 13 and CPF 14, right. Then CPF 21, CPF 22, CPF 23 and CPF 24, right. Then CPF 31, then CPF 32, then CPF 33, then CPF 34, then CPF 41, then CPF 42, then CPF 43, then CPF 44. Then what will come here? Here it will be delta PL1, delta PL2, very easy it is, delta PL3 and delta PL4, right. That means suppose this delta PL1 actually that power demand of distribution company 1, it has contact with your GenCo 1, then GenCo 2, then GenCo 3 and GenCo 4, right. If you look into this, if you I mean this contact has a delta PL1 GenCo this GenCo 1, it has contact with GenCo 1 is this much, right. If you look into the disco 1 has contact with the GenCo 1, then disco 2, right, it has contact also with your this GenCo 1, that is CPF 12, then distribution company 3, it has some contact with this one which that is CPF 13, and distribution company 4, it has contact with this one. That means if you multiply this one, it will be your what you call, this will be power generated by this thing, that is this is GenCo 1, GenCo 2 like this, and this side if you make delta PL1, delta PL2, delta PL3, delta PL4, therefore this that whatever disco 1 has the contact is CPF 1 or GenCo 1, disco 2 is CPF 2 delta 2 GenCo 1, disco 3 CPF 13, this much of fraction with GenCo 1, and disco 4 CPF 14. Basically, if its demand is delta PL1, then GenCo 1 has to supply the delta PL1 into CPF 1. Disco 2 has contact with your what you call delta PL2, so and it has contact with GenCo 1, so CPF 12 into delta PL2. Then plus disco 3 also has contact with GenCo 1 and fraction is CPF 13, demand is your delta PL3, it will be delta PL3, and disco 4 suppose its demand is total delta PL4, but fraction is contact with GenCo 1, it will be CPF 14 into delta PL4 rather, right. That is why this delta, that means total power generated by GenCos at the steady state, it will be CPF 11 delta PL1 plus CPF 12 delta PL2 plus CPF 13 delta PL3 plus CPF 14 delta PL4, right. This way, that means delta PL1, suppose this matrix is known to you, this delta PL1, delta PL2, delta PL3, delta PL4 is also known to you, then automatically you can calculate delta PG1 SS, delta PG2 SS, delta PG3 SS and delta. So, numericals I am not showing, but you can generate your thing, but only thing is that summation of all these column elements should be 1, this should be 1.0, summation of all these column element, summation should be 1, you have to be careful when you take this, right, and you can create your own matrix, right, and you take some delta PL1, delta PL2, delta PL3, delta PL4, then you will know how much this GenCo 1 will generate, GenCo 2 will generate, GenCo 3 will generate and GenCo 4 will generate, right. Many other issues are there, but as it is a as it is a BTech course 3rd year and 4th year, and that is why simulation and other thing regarding this thing I have skipped it, it is not required for you, only this understanding will be more than enough, right. So, that is why this matrix is given, and how does and GenCo 1 generation, actually this one it is already given here. So, easily you can make it, right. I will see that in the assignment or something this kind of problem can be given when that thing will come, right. So, with this that load frequency control, right, we are concluding here, and then we will take that another topic, that is your unit commitment. First thing, let me tell you regarding unit commitment, it is actually huge topic, but I thought at least you should know little bit, right. Many issues are there, and it is almost impossible to solve problems in the classroom, right, but something will be given. If something is given, then easily you can solve it. But if you try to find out that actually unit commitment in general means that although several issues are there, several constants are there, right, like your startup, shutdown issues are there, many other constants are involved in that unit commitment. Suppose in a in every hour, that if you consider hourly load variation, then every hour you will find loads are changing, right. Every hour you will find that load demand is changing. That means every hour you have to change the generation. Suppose in a power plant you may have 5, 6 or 7 generators, say. So, you know that which generator is most economical of generating power, because generator, that fuel cost characteristic are different, assuming that they are not identical. So, in that case what will happen, that suppose today at this moment, suppose that power demand is say 1000 megawatt, right. So, I have the unit that whose total installed capacity, say it may be 1500 or 1600 megawatt. That means total generation capacity having more than your load demand, right. The idea is that there is a possibility of routine outage or force outage of the unit due to fault or something else, right. So, therefore, I have to pick up that which generators should be involved to generate power and how much, such that my operating cost will be minimum, and how many units will be committed for that, right, and that is unit commitment. Suppose you are supposed to supply 1000 megawatt, you need not run that your what you call all 5 units. You may have suppose if you have a large 3 or 4 units may be sufficient if you have 6 or 7. And another thing is that unit commitment issue, actually it is coming for the your what you call for thermal power plant mainly, because hydropower case, that hydro generation can pick up very quickly, right, and it can meet the load very quickly. But in the case of thermal power plants, it actually takes your what you call just to from the starting to your what you call generating power, it may take 2 to 8 hours, right. This is one thing. Another thing, for the shutdown case also, that thermal power plant just you cannot shut down immediately, right. Then this is a question to you, that it is a very interesting question. Suppose a thermal unit is there and it was running, say it was just suppose its rating is say for example 250 megawatt, for example, say a rated capacity, and suppose you want to shut down it due to some reason, right. And question is that how many second, minutes or hour it will take to completely shut down, right. It is an interesting question, I know. You have to think and you have to answer this, that suppose I want to bring that whole generator turbine generator system to a standstill, right. So, how many hours it will take? Of course, not minute or second in any way, it is hours. So, how many hours you are expecting to bring it to the 0 speed, and what is the reason? Why it will take long time, and what is the reason, right. So, this is a question to you, and suppose you have, before going to this, mathematics is very less here, but understanding is more. Suppose you have 5 units which is supposed to supply power 1000 megawatts, say at this moment, and suppose my 3 units are operating and supplying power. So, in that case other 2 units, say it was in standstill, that means it is not under no load condition or not running. So, if sub shutdown is there of the unit, so in or sudden load increase also, both can happen, right. So, those generators cannot supply power. Suppose 2 units shut down, then one generator cannot supply 1000 megawatt, then in that case you do not have any spare unit also or your spinning unit, such that you can connect it and supply the power. That means easy solution is the load shedding. But suppose if you have that hydro generation, right, hydropower generation, then in that case hydro you can bring it to the your what you call operation, such that it is connected to supply the load, because hydro can pick up the generation very fast, right, and I mean very quickly it can pick up the generation, right. So, in that case no problem, but assuming that hydro generation is not available. So, in that case you have to you have to see that this is a very and what you have to do is actually, this is basically it is a if you have a lookup table, that in which hour which unit will operate, such that your what you call that operating cost will be minimum, because whatever power you generate, everything is okay, but one thing is there, as far as suppose if you have your own industry, you will also look into the profit, nothing else, right? It is a business. So, in that case you have to see that economy, that what will be how can I can minimize the cost of power generation such that I can make more profit, or in other way also I can your sell power at the cheaper rate, right. So, unit commitment is a huge one. There are several techniques are there to solve such problem, but it is a very time consuming process, but we will see the simple thing, right. We will see the simple thing such that you can have some ideas about the unit commitment, right. So, first thing is that unit commitment actually it is not economical to run all the units, right, available all the time, because there is no need to run, because it may not be economical, I told you. Second thing is to determine the units of a plant that should operate for a particular load is the problem of unit commitment, that how many units you will be operating for supplying a certain load. That means every hour there is a possibility that new unit, some unit may be what you call may be connected to supply more load, or some unit maybe it will be or what you call it will be running and suppose but almost at no load, right. So, but it will be spinning, because if you shut down any unit for thermal units, it takes long time to start. I told you that at least 2 to 8 hours. It is because it is a huge dynamics, boiler is also involved, and boiler dynamics is very slow one, right. Boilers, economizer, I mean those dynamics actually is very slow dynamics, it takes time, and lot of non-linearities are involved also in that what you call AGC. I did not tell those non-linearities, only I have mentioned, right. I believe that for undergraduate level things are okay, but many constants are there also, right, and security is another issue for unit commitment. So, this problem is of importance for thermal plants, I told you, right. As for other types of generation, I told you, such as hydro, the operating cost and startup times are negligible for hydro as compared to the thermal power plant, right. So, that their on off status is not important for, so therefore, for hydro generation that on off status actually not that important, but thermal it is very much important. A simple but suboptimal approach to the problem is to impose priority ordering, wherein the most efficient unit is loaded first to be followed by the next efficient unit, which is in order as load increases, right. So, in that case what will happen, suppose one very complex, very time consuming way, but suppose you have so many units, suppose 5-6 units are there, suppose to supply a particular load, if you go for all sort of combinations, it will be a huge computation, right. So, but we have to avoid that, and out of this huge computation you have to see which combination is giving you most economical operation. So, that is why a straightforward but highly time consuming way of finding the most economical combination of units to meet a particular load demand, that is to try all possible combinations of unit that can supply this load. So, it is a very time consuming process, right, if you try for all possibilities. To divide the load optimally among the units of each combination by use of the coordination equations. That coordination equation or little bit we have seen in the previous course, power system analysis, that optimal system operation, right, we have seen, and many good problems we have solved also, that you have also done, right. So, as to find the most economical operating cost of the combination, right, then to determine the combination which has the least operating cost among all these, right. So, it is a very unit commitment actually is a very your what you call very time consuming process. So, considerable computational saving can be achieved, either you can use branch and bound, here we will not see, or a dynamic programming method, we will see little bit on dynamic programming here, but all calculations cannot be done, right. Just I will show you that how can we do it, some flavor will be given, right. So, for comparing the economics of combination, as certain combination need not be tried at all, because there are certain combinations where you will find that things are very complicated, right. I mean not complicated, that is your what you call that cost of operating cost is very high, right. Then dynamic programming method, although it is also there are many other methods are there, but only dynamic programming I thought little bit I will tell you. Soft computing techniques are available nowadays, right, and it gives I mean very good results, but some soft computing also takes a lot of time, but it gives the nearly global optimum result, nearly global optimal or best result, right. So, in a particular problem the unit commitment table is to be arrived at for the complete load cycle. Load cycle means suppose 24 hours load curve you have. So, first hour, second hour, third hour like this, right. and if the load is assumed to increase in small but finite size step, and we are taking the load is increasing in discrete step. In reality, of course, it is not true, but we have to we have to follow certain methodology, right. So, dynamic programming can be used to take advantage for computing the unit commitment table. And where I am telling unit, you see means unit commitment. Unit commitment table means you have to make up a table, first hour how many units, second hour how many units, like this, right. It cannot be online problem, right. If you have everything, if you know the demand, forecasting demand, everything if you know, so you can prepare this optimum unit commitment table, wherein it is not necessary to solve the coordination equation. So, in this case coordination equation is not required, while at the same time the unit combination to be tried are much reduced in number. For this reason only the dynamic programming approach will be advanced, or only little bit of dynamic programming thing we will see. The total number of units available, their individual cost characteristic and the load cycle on the station are assumed to be known a priori. That means, this fuel cost characteristic, it is available from the manufacturer, it is available, right. And we are assuming that your load cycle, that means load cycle, load curve is known to us, right. The load curve is given, that forecasted load whatsoever is given, unless and until some unusual event happened, right, then loads will follow the same thing, right. So, further, for example, suppose if some important final match is going on, maybe football, maybe cricket, whatsoever, at that time we will find that all TVs will be switched on. So, at that moment, that hour, right, those hours, that power demand will increase, right. So many issues are there. So, further it shall be assumed that the load on each unit or combination of unit charges is your suitably small but uniform step of size, that delta megawatt. That means, we will see that changes in power load, it will taken delta megawatt. I mean very small size, say a step of 1 megawatt, say, that is why I put delta in bracket, I have made megawatt, delta megawatt instead of delta PG, right. So, starting arbitrarily with any 2 units, you start with any 2 units, the most economical combination is determined for all the discrete load levels of the combined output of the 2 units, right. First we will take 2 units, then we will add another one, third one, fourth one, like this, and there is no question, that is your the way will unit number 1, 2, 3, 4, it is arbitrary. It is not like that I will first most efficient, then second most efficient, nothing like that, just arbitrary, right. So, at each load level the most economic answer may be to run either unit or both units with a certain load sharing between the two, right. First we will start 2 units, maybe between the 2 units, maybe 1 unit will be economical also, right. It is not necessarily the 2 units will run, right. For example, suppose load is 50 megawatt, 2 units you are tried and you find 1 unit generating 50 megawatt is most economical, that also possible. Even 2 units are possible, say 1 unit may be generating 30 megawatt, another may be 20 megawatt increase, right, that is also possible. So, the most economical cost curve in discrete form for the 2 units thus obtained. Suppose that data little bit I will show you, that it will be available, can be viewed as the cost curve of a single equivalent unit, that we will see. The third unit is now added and the procedure is repeated to find the cost curve of the 3 combined units. Actually, this dynamic programming, yesterday 4, 5, 6 pages, I think all calculations are made. Then I found I will not show these calculations here, because it will be very hectic. So, I will show only 1 or 2 small thing how to make it, right. So, it may be noted that in this procedure the operating combination of third and first, or also third and second also, are not required to be worked out resulting in your what you call considerable saving in computational effort. Suppose 1, 2 unit, suppose first 1 or 2 units are operating and you found that their combination, optimal combination, when third unit is added in dynamic programming, you need not consider again 1 and third and second and third, no need, actually there is no need, right. So, this way some computational efficiency can be achieved, that means effort of computation will be less. The process is repeated till all the available units are exhausted, and you have to consider in this way all the units, right. The advantage of this approach is that having obtained the optimal way of loading k units, this is k units, right, it is quite your what you call easy to determine the optimal your what you call here actually optimal manner of loading k plus 1 units, right. So, basically what happened that one after another, suppose you have k number of units, just you are considering first 1 and 2, then third, then fourth, like this way up to kth number of units, right. So, this way you can test and you can find out what will be the best combination. Thank you.